Hello, and this is our second installment of Unit 10. This is on plate tectonics. This is my physical geology class, and should have actually ended the first section with this slide. We're going to do practice exercise 1, where we're going to actually use cutouts of the continents first, and then the continents with a picture to actually try to put together Pangea, which was whole Earth, and this was actually brought about with Alfred Wegener when he started noticing the shape of these continents as maps got better and better, higher resolution. Started noticing that South America and Africa, North America and Africa, Greenland, North America, and Europe and Asia, and then India, Antarctica, Australia, all sort of fit together. We have polar areas, tropical areas where North America was pretty much located at the tropics. Then we actually moved into the next one where we started talking about when the Pangea started breaking up. It started breaking up north-south first, and we had Laurasia and Gondwana land. And basically what happened is we had divergence, land before time. If you remember Littlefoot, and I don't remember what this Triceratops, Tracy or somebody, and they started noticing earth shakes, and they noticed that the ground opened up, and pretty soon the ground opened up so that some of the dinosaurs on this side and some of the dinosaurs on this side could no longer walk across, jump across, and only the flyers could go through. And then soon after that, they should have actually shown an ocean opening up, and we'll actually see that these things will get far enough away and then even the birds have a tough time, or the flyers have a tough time. 150 million years ago for this breakup. And then eventually the Atlantic Ocean starts breaking up between South America and Africa, and then we get an Atlantic Ocean. And as the Atlantic Ocean gets larger, the Pacific gets smaller. Wegener's evidence. He started with Pangea. First thing he started noticing is that we found fossils between South America and Africa of this crocodilosaur. I forgot its real name. I just call it a crocodilosaur. But basically, if Pangea was there, it was very easy for him to swim across this body of water. Crocodiles are more freshwater critters. They're going to spend more time in the Amazon River. They're not going to really swim across South America to Africa to a saltwater environment. They can handle salt water for a little while, but not for a long trip. But if these things were closer together, it's very easy to see why we have fossils of them in South America and Africa now that they're 4,000 or 5,000 miles apart. We have plants that actually were tropical varieties. South America, a little closer to the rainforest, I can see that. This part of Africa, maybe a little higher, I could see it. I could see it in Madagascar, I could see it in India. Tough to see it in Antarctica, and tough to see it pretty much anywhere in Australia because it's a desert island as well. We have a dog size, I forgot what this guy's called too. This is coming from 2 years of teaching biology. But this is a dog-size dinosaur, probably not a real good swimmer, plant eater. Africa, India, and Antarctica, and in Antarctica. I can't really see this thing. It could have actually crossed Africa into Arabia, and then down across the Himalayas into India. But if that were really true, we'd start seeing these fossils in other places. They're in a relatively thin band. And again, I don't see them in Antarctica because the plants, well, there were plants, but I don't see the plants because it's so cold, and I don't see plant eaters because of that. And then we have other ones that obviously not swimmers that are found on opposite sides of the ocean. Also, we found mountain ranges, Caledonian Mountains up here in Greenland and up here in Scandinavian countries, as well as the British Isles. They are actually move into Canada and the Appalachian Mountains and the mountains, what are these called? Well, these mountains over in Africa, they're made out of the same type of rock. They're the same age. They're the same kind of mountain range, and it was actually when these two continents slammed together to make Pangea. But now they're on opposite sides of the ocean, which is really weird. Rock similarities in terms of age and also in terms of igneous, sedimentary, and metamorphic. We see them across the ocean. and they match up pretty well if we put South America and Africa together. Glacier evidence, where we actually see glacier evidence in Africa, the desert of Africa, which is a little weird, but the glacier evidence actually shows us that it moved this way towards the tip of of Africa, and it also moved this way into the continent. And glaciers don't move toward continents; they move towards ocean. They go downhill just like water does, and water doesn't flow into the continent of Africa. Same thing for South America; it doesn't flow into the continent it flows out of. Antarctica, I can see it. India, not supposed to have it. Australia, not supposed to have it, but again, actually moving towards the continent. And if we take a look at the map, this is where it lasts, or where these things are located today. But if we put these continents together, we actually get to see them, that it actually seems to fit. Tropics, desert, and glaciers. If we take a look at the location of those on large land masses, we see glaciation, we see a desert, even though this part of Africa, that part of South America is not a desert, it's a rainforest, but the rock underneath it says that it was. And then we can move up into the tropics, which, it shouldn't be quite that high into South America. And same thing with India and Australia with that cold glaciation. And then one of the really strongest scientific method, if you take a look at rock in North America, you look at rock in Asia, you look at rock in Africa, a lot of times the rock has small iron material in it, ferric molecules, and these things actually, if the material is liquid, they'll align themselves to the present north-south orientation of our magnetic poles. And if you take a look at the ones in North America and you look at the ones over here in Greenland and Iceland, and you look at all of them, they're going all over the direction. They're pointing and they're curving. They are pointing towards the North Pole, but they're actually curving all over the place. But if we move them into Pangea, the lines straighten out and they look like they're going to an original common pole, where these may look like the pole is dancing around a little bit. So moving the land masses to Pangea is actually aligns itself with fossil evidence, climatic evidence, rock, and in terms of geology and age of rock and climates and magnetic paleomagnetism, old magnetics, all point to the fact that this was a large landmass that Wegener saw. Plate tectonics says that the Earth's crust is divided into 12 major plates. These are both made out of continental and oceanic crust. Plate motion causes them to collide, come together, pull apart, tension, and scrape against each other, the shearing forces that we talked about in earthquakes. Each type of interaction causes characteristic type earth structures or tectonic features, and the word tectonic or tecton actually refers to deformation of crust and the consequence of the interaction. That's why we're calling it plate tectonics. The plates interact and they deform. The world's plates, if you take a look, these are the large plates. Notice that they are made up of continents as well as ocean floor. This is the mid-ocean ridge. We have convergent boundaries. We actually have shearing forces as well. And if you take a look at these little breaks, this is sort of like if you break an egg or you try to peel an orange all in one place, you're going to get a zigzag pattern. And the Earth is a sphere, breaks sort of the same way. These zigzag patterns, these are the divergent areas. These rounder type materials, these are convergent areas. We actually just had a really bad earthquake as the Indian plates running into Asian plate in Nepal. Right about there, we had a 7.8 Richter earthquake, which the death toll, I think I saw today, and this is Saturday, it's already reached about 2,000. It probably will. And I don't know how many missing. We'll actually find out some of those missing are also going to be increase the death toll. But we have some that are all oceanic. We have some that are really small. We have some that are relatively large. This is the Pacific plate, the dying plate, as North America pushes over it. This Juan de Fuca plate and this Cocos plate used to be a lot larger. These are divergent areas, and it's pushing this Juan de Fuca plate towards North America, or the Cocos plate towards this Caribbean plate, and we're actually building a really good convergent zone. Eventually North America will continue to go over the Juan de Fuca plate, and this break right here is one of these side-to-side breakage of the divergent area that now is the San Andreas Fault. It spends a little bit of time on this really west coast of the United States up through Baja, California, Los Angeles, and then comes out into the ocean at San Francisco, and then moves up towards Alaska. This part of California is not going to drop off into the ocean. It's going to continue to move in this direction up along Canada and eventually run into Alaska, but that's 450 million years from now. So we've got lots of plates. Most of the plates, tectonic plates, are made up of both oceanic and continental crust, and they take the name of the large land masses or the Pacific Ocean that sits on top of it. What makes up a tectonic plate? They're made up of the lithosphere. The lithosphere is made up of the crust, and notice that the crust is thickest under the mountains and thinnest under the mid-ocean ridge or the oceans. So we have very thin crust on the ocean. We have thick crust where it's continental, even when it's really flat and low, like in the middle of the United States, and incredibly thick. Skip these files. And then it's incredibly thick underneath the mountain ranges, so like the Rocky Mountains. Oceanic lithosphere is typically 50 to 100 kilometers thick. In the regular ocean, so like this material, mid-ocean ridge may be a lot thinner, maybe only 2 or 3 kilometers. Continental lithosphere is thicker, up to 150, but it consists of about 50 kilometers of the crust and 100 kilometers of the upper mantle. So the lithosphere is made up of the crust, this black part of the ocean, this gray part of the continents, plus the area that's underneath it, which is the upper mantle, and those are the tectonic plates. What lies beneath the tectonic plates is the asthenosphere. It is a more liquid part of the mantle. I don't really have a really good picture, but we've got continental crust with soil on top of it. We have oceanic crust. We have the upper mantle, which makes up the lithosphere, and the section below it is called the asthenosphere. In the asthenosphere, we actually have these convective motions where the crust sitting on top, the lithosphere, the mantle, and underneath the core, producing bunches of heat, heat making material rise, and as it hits the crust, it diverges and it actually pulls on the crust. The crust also sinks in places where two plates collide, and we may get this material that actually pulls the crust down. It's called slab pull, and it's all driven by convection. And then what happens at the tectonic boundaries? Well, we get them pulling apart, causing tension. We get them coming together, causing compression, and we have them moving side to side. The shearing forces we talked about in terms of earthquakes, and shearing boundaries happen at these offset of the divergent areas. Divergence happen at this mid-ocean ridge, right along the middle of the two plates, and that's a plate boundary. And the convergence actually happens when the oceanic crust runs into something that is not as dense and gets pushed down. It's subducting, which we'll talk about later. And that is the end of the second section of this Unit 10 Plate Tectonics. Thanks for stopping by.